Alright, welcome back. So in the last few videos we went over applied examples with like springs and everything to solve homogeneous differential equations, which were of the form like constants times the second derivative, first derivative, no derivative, but it equals 0. And that's what it means to be a homogeneous equation. And in these applied examples with springs, we'd have like the mass m, damping constant c, spring constant k, but generally just constants a, b, and c. Now this unit is all about non-homogeneous equations, which means it's what we had before, but it no longer equals 0. It equals some function of x. So it can be x squared, cosine of x, anything. And in this example, it's actually going to be 2e to the 3x. But we're going to get to that soon. But what we actually end up doing to solve for this is we treat it as a homogeneous equation first. We solve it, we see what we get, and then we use clues from our solution to that, which is called a complementary solution, which is yc. And then with that, we'll solve for a particular solution. And once we have both of those, we add them together, and that's our final solution. So when we're solving for our particular solution, one thing I want to just point out is we're going to be quote-unquote like guessing, where we know that no matter how many times we derive e to the 3x, it's always going to have e to the 3x in it. It's just a constant in front that's going to change. If we derive this once, 2e to the 3x, we derive it, we get 2e to the 3x times 3. Do it again, we get 2 times 3 times e to the 3x times 3. It's just the constants in front that change. So our guess, we're just going to have a. And we derive it, we know it's going to be 3 times a e to 3x. And that is going to be like y prime, or this is y. We derive it again, we get y double prime equals 9a e to 3x. And you'll see how that becomes helpful soon enough. But first, let's find our complementary solution. So what we do is we treat this as what we've been doing before. We've done it a million times by now. We just treat this as a homogeneous equation where it equals 0. And the beauty about that is we can just factor it, r squared minus r minus 2r, minus 2, and we get negative 2 and 1 is factorable, so r squared plus r minus 2r minus 2r, r plus 1 minus 2r plus 1. So we get r plus 1 and r minus 2. So we get r1 equals negative 1, r2 equals 2. And r1 doesn't equal r2, therefore we have distinct roots. And the equation for distinct roots is say y of x equals c1 e to the r1x plus c2 e to the r2x. If it was repeated roots, we just have a normal r up here, and then we'd have an extra x here. But not for now. So let's plug in our values for r1 and r2, and we get negative x and 2x. Now, what I mean by saying we use the complementary, this is our complementary solution. We already found that. What I mean about using this for clues to find the particular solution is, say this was e to the 3x. And, well, we're adding the particular solution with the complementary solution. And we know that the complementary solution is in some form of a constant times e to the 3x. So what happens if we add this with what we had before, c2? Well, we just get a plus c2 of e to the 3x. And this is still just some constant. So it doesn't change anything. So if we did end up having something that repeated here, we would actually have to multiply this by an x. And then we'd have like a product rule here, and it would be a lot harder to derive. But we're going to do that in future examples. But for right now, it's just an interview to how to solve these problems. So I picked a pretty easy one. But this is our complementary solution YC. Now, for YP, there's YC right here. For YP, we use our guess where f of x, this non-homogeneous part, equals 2e to the 3x, right here. And we create our guess. We know it's going to be some constant times e to the 3x. And, well, we know that this equals itself times c plus the derivative of itself times b plus the second derivative of itself times a. So what we're going to do is just use our guess. We derive our guess, and we derive it again. And we have like a general idea of what this function and its derivatives look like. But in order to find a, we need another equation. And what's beautiful is we already have that equation. So we're actually just going to plug some stuff in. This is our equation, sorry. So we have y double prime. We know y double prime is 9a e to the 3x minus y prime, so minus 3a e to the 3x minus 2y, so minus 2a e to the 3x equals 2e to the 3x. And, well, we can just divide this all by e to the 3x. We get 9a minus 3a minus 2a equals 2. So we get 4a equals 2. Therefore, a equals 1/2. So we get y equals, or yp equals 1/2 e to the 3x. That's our particular solution part. So by doing that, we found what a is, and now our guess is no longer a guess. We know this as a fact. And our final solution is just this plus that. So y equals c1 e to the negative x plus c2 e to the 2x plus 1/2 e to the 3x. We're going to jump into some harder questions where we will need to change the particular solution based on what we get for the complementary solution, but just wanted to do an easy one to get us started. And if it doesn't make sense now, hopefully after a few examples, it'll make sense soon enough.